that we're going to use to build the area is we're going to realize that, and we're told to use right endpoints. We're going to use the idea that I could chop this up into rectangles. And why rectangles? Well, I know that the area of a rectangle is what formula?
Length times width.
Length times width. Okay, so I know how to find the area of a rectangle. I don't know how to find the area of space under the curve x squared plus 7. So if I chopped it up into rectangles though, I could just find the length and width of this rectangle, and find the length and width of this rectangle, and find the length and width of this rectangle, and so forth, and multiply the lengths and widths, and then add them together. And I would get an estimate of the area under the curve. The length of the rectangle, or the height of the rectangle, because it might not necessarily be the longer side if you use length. So the height of each of the rectangles, notice, is a value of the function. Okay, so if this is x equals 2, then, wait, no, I think I skipped by 2, so I think this is x equals 4. This is x equals 2. So where x equals 4, the value of the function is telling me what height this rectangle is, and then I set my window from 0 to 12, and I skipped by 2, so the width of any rectangle for the rectangles I made is 2. Okay, so the area of this rectangle is 2 times 4 squared plus 7, or 2 times 16 plus 7 is 23, and 2 times 23 is 46. Okay, so the area of this rectangle is 46. Does everybody understand how I found the area of that rectangle?
Yes.
All right, so the area of this rectangle is going to be 2 times 1 squared plus 7, which would be 2 times 8, or 16. So the area of this rectangle is 16. And the area of this rectangle is 2 times 6 squared plus 7, which is 2 times 36 plus 7 is 43, right?
Yeah.
So that would be 86. And so forth, until I got to the last one. Now, my sum, I guess why don't we go ahead and finish finding the rest of them. So this would be, because all of them are with 2. Okay, so this would be 2 times 8 squared plus 7. So it's 2 times 63, so 126. And this is 2 times 10 squared plus 7. So it's 2 times 107, so it's 214. And 2 times 12 squared plus 7, so 144 plus 7 is 150, sorry, 150, 6 is taken, 151, yes. And so that would be 302.
What made you choose
Your 8 is not right.
And say 8 squared, 64.
Oh, yeah.
Yeah,
8
plus,
squared
yeah,
is
so it's gonna be 71.
Yeah, I don't know what I was doing. Okay, so 64 would be 7.
First question.
So 142. Is that the only one that does?
Do we even know what 8 squared is?
Yeah, I don't know what I, sorry, I don't know what I was. Oh yeah, I did 6 twice, sorry. Okay, so our estimate then, so the total area estimate would be 16 plus the 46 plus the 86 plus 142 plus 214 plus 302. And let's see, 18, 20, 26, 6, and 8 is 14, 18, 19, 2, 4, 7. 796 would be my estimate of the area. And it's an overestimate. Can you guys see why I'm saying it's an overestimate?
Yes.
Yeah.
Because there are these extra little sections that are not really part of the area underneath the curve.
I think the area.
That brings me to my question, is why didn't you choose smaller increments to make it more accurate?
Very good. It's almost like you and I coordinated as to how we
Well,
were
this
going
is
to do
how
the
signals are
discussion.
digitalized, when it comes to digitalized.
I'm sorry, what is digitalized?
Well, when you take a signal and put it into make a digital form, it's
Uh-huh.
the same kind of concept. If you break it down, it's not gonna be as accurate as the more text.
Oh,
you
that's
take on
interesting.
it.
That's an interesting application.
Yeah.
I like that. I mean, I think I'm interested in, yes, Xavier.
Your area total is off. You
Is my area total
Yeah.
off?
You
Sorry.
missed the 1 and the 16 when you counted. So
I missed the 1 and the, oh, okay, so 3,
The-
7, 15, 19, 20. So 3, 4, 5, 8. Is it?
yeah.
Right, okay, okay, so as Josh was just Xavier, thank you. As Josh was saying, we kind of have a bad estimate, we at least kind of built the idea. We know we have an overestimate, but we could get a better estimate if I made smaller rectangles. Okay, so just for starters, if I at least cut them so that they're only width 1, for example, you can see that sorry, I'm stuck today. But you can see by just even making them with 1, it's fitting the curve better. But we could get an even better fit if I made them only a half wide, or a fourth wide, or a 32nd wide,
Infinitely
etc.
better.
So we're in calculus class, and the very first topic we covered was about limits. And limits really, when it comes down to it, is the idea of starting a pattern and keeping that pattern going on sort of forever and looking to see if there is some final result. Okay, so if we at least are kind of recognizing the idea that you could get a better and better and better and better estimate by making your rectangles skinnier and skinnier and skinnier and skinnier. If you make the rectangles skinnier, what happens to the number of rectangles? It increases, okay?
So it's a.
So n's going to be my number of rectangles. Okay, n's going to equal the number of rectangles. So what I'm doing right now is by the time I get done writing over there, I'll have defined what a Riemann sum is, okay? This symbol is the Greek letter sigma. It's the capital Greek letter sigma. You may have seen it on Excel. It's like the symbol Excel uses to tell you to do what? Sum, right. Okay, so what did we do with all of these individual areas? We added them up. So we're going to be adding areas of rectangles. The width of the rectangles, okay, the very first one that I drew, and actually I still have all the numbers up here, I kept using a width of 2. Think about the arithmetic I did to get a width of 2. I was going, oh, you know what, I think in the problem we're going from 0 to 10.
Yeah.
Sorry. Anyways, but from now on, this point forward on the problem, we'll go out to 10. Okay. So I still am going to have a width of 2. Okay, for my first rectangle. So 10 is where I'm stopping. 0 is where I started. Do you understand what I mean by that? 10 is where we're cutting it off. 0 is where we're starting. And if I go from 0 to 10, skipping like I originally was, 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, I have 5 rectangles. So the width of the rectangles is where you're stopping minus where you're starting, divided by however many rectangles you are going to end up using. So my first example, I technically used 6, but that's because I was going from 0 to 12. If you cut them all in half and we'll go from 0 to 10, it would be 10 rectangles. Okay, so this is giving me the width of the rectangles. The height of the rectangles is given by the function, and in the directions you're told to use the right endpoint. Okay, so I'm going to redraw it with the original width of 2 rectangles, okay? So here's my first right endpoint at 2, starting at 0. Here's my second right endpoint at 4. Here's my third right endpoint at 6. Here's my fourth right endpoint at 8. And here's my fifth right endpoint at 10. So we know we're going to plug these numbers into my function. And my function was x squared plus 7 was my function. But we need to figure out what to plug in here because every rectangle has a different right endpoint. I need to come up with the pattern that accurately will give me whatever right endpoint I happen to be on as I move from rectangle 1 to rectangle 2 to rectangle 3. So this was rectangle 1, its right endpoint was 2. Okay, so rectangle 1 led me to a right endpoint of 2. Rectangle 2 led me to a right endpoint of 4. Rectangle 3 led me to a right endpoint of 6. Rectangle 4 led me to a right endpoint of 8. And rectangle 5 led me to a right endpoint of 10.
So 2n.
It's 2n, exactly. And 2 happens to be the width of the rectangles, okay? So I'm not going to write 2n here because the 2 is specific to us having only 5 rectangles.
Right.
So 10 over n is the width, because I don't really need the minus 0. I just put the minus 0 to show in general that you get the width by taking where you stop minus where you start divided by number of rectangles. So for this one, that reduces down to 10 over n. So 10 over n is the width, again. The x value, when I use right endpoints, and I start at 0, okay? So for this one, we started at 0, is going to be the width times whatever rectangle I'm on. So Brian said 2n, which was fine. I mean, I understood why he said that. N technically is the total number of rectangles I'm using. The reason why I put another variable I is the counter for what rectangle you're currently on. Okay, n is the total number. So for my first example, or the example that's drawn on the board, n is 5, but I goes from 1 to 2 to 3 to 4 to 5. So if you were writing a program, I would be, in the loop, incrementing in the loop. I just wrote the Riemann sum, but what this notation means, this means what are you going to start your counter at? What are you going to stop your counter at? So I'm starting my counter at 1, I'm stopping my counter at n. My example that's drawn over there, I start at 1, I stop at 5. But I've written it in general. So this is the Riemann sum that represents the exact area between the curve and the x-axis. And it's the Riemann sum for the exact area because I put the little bit about the limit as n goes to infinity. I could actually stop at a specific n, like say, okay, you know, I'm gonna chop it into 100 rectangles. By the time I do that, the amount I'm gonna be off is so small that I'm not gonna worry about it, okay? So that would look like, no, I'm missing a parenthesis. Okay, this would be the approximate area using 100 rectangles and right endpoints. Okay, it's not gonna give me the exact, but with 100 rectangles, it might be pretty close. Whereas if you want technically the exact area, then you wanna add the bit on the front that the n could go to infinity. And as the number of rectangles goes to infinity, the width of them is going to 0, and you would be fitting the curve exactly. And it seemed, like at first exposure, you might think, well, I can't really send n to infinity because my width can't really be 0. Because, I mean, it's one of these like little Zeno's paradox conundrums. It's like, well, if the width of them are 0, what's going to be the area of any of the rectangles? 0. So it's like, well, how can I get any area at all? But you actually can algebraically work these out, and you do get a number. You get an answer that does represent the area under the curve. Okay, whether we do that algebra tonight, I don't know. I'm more concerned about building the concept at the moment. But we will work some out. And I have, if you look through your packet, I've got an example all worked out using midpoints, which purposely makes it messier. And my point of that is just to show you, look, these always can be worked out. They just can get messy. Before I talk anymore, does anybody have any other questions? Before we add more to the idea?
These eyes